Hello. I reviewed how we apply the statistical methods to the example that I gave at the beginning. And from now on, we are going to review more seriously, review statistics and what you learned in 320 more seriously. The first step is to review the probability framework, the definitions and notations for probabilities and the basic statistic terms. So there are 4 review chapters, and we are doing the first one. And within the first part, there are 4 small sections. Let's go to the first one. Population, random variable, and distribution. So first, population. It is very important to understand the difference between the population and the sample. So population is everything we want to like. So the group that we want to know, everyone in the group that we would like to understand. For example, in our previous example, the population is every school or every school district we are interested in. If you are a California governor, then school districts in California. But say I'm the New York State, say Secretary of Education, then I would be interested in all the schools in the New York State. So, uh, so depending on what you are interested, and then population is automatically set. So you are the ultimate goal. Ideally, if you observe everything in the population, then you are good. You don't need to worry anything more than that. You don't need statistics at all. So once you know all the population, then there is no random error. There is you know everything. So it's just a matter of computation. And in our framework, we are going to assume that the size of the population is infinite because it does not matter. Because if you know the population, you don't need statistics. It's just computation. So we are learning, this is a statistics course. So our implicit assumption is that we don't observe the population, right? So like for example, think about the presidential election. Once all votes are open, it's just a matter of computation. There is no estimate, there is no probability, right? There is no errors, right? So once all the votes are open, there is no more guessing, no more estimating. But until the votes are open, fully open, you only observe part of them. For example, political polls are just small portion of voters, and until the votes are fully open, you see updated probabilities of winning, probabilities who's likely to win, like right. So estimate number of seats for each party. So they are estimates, they are statistics, because the population is not open, population is not fully known. So in that sense, we have to assume that the population is not observed, not fully observed, but only a part of that is observed. The observed part of the population is the sample, that is the data, that's what you observe, your observations, right? But still, we will keep the population in mind because we always assume that what we want to know is the population, right? It's a imaginary but necessary target. And then random variable is a numerical summary of the outcome, numerical description of the outcome. In our case, how do we describe students' educational outcome? There can be different measures, but we are going to use test score, right? You may use different scores or different measures, but anyhow, you have to have some numbers, and you have to have one or two. Like can be multiple, but typically one number should summarize that. Also, student to teacher ratio is another measure of class size. You may have different measures, but anyhow, you have to define that and the numerical description of the outcome is a random variable. So you have to imagine this. There are infinite number of school districts you are interested in, you want to know, and you are choosing one of them at random. You are randomly choosing one of them and choose one school district and observe its average test score and average and the standard teacher ratio, student teacher ratio. So these two are random variables, and these are random. Those two outcomes are random because if you choose a different school district, you are going to observe a different outcome. Right? That's how it works. And when you assume that, if you assume that the population is observed, fully observed, then you can think about the distribution of the population. Right? If you have if you observe the infinite number of school districts, you can calculate probabilities. What is the probability of the school districts have an average test score of 650? But also you may consider probability of the school district average test score being greater than 640 but smaller than 660. So these probabilities are easy to calculate if you observe everyone, right? If you observe the population, the probability is just a matter of computation, easy to calculate. And one thing I would like to add here is this probability looks more intuitive, but it is not well defined for continuous random variable. When a variable is continuous, this probability at one point always 0. So this approach does not work with continuous random variable. So we would like to use something like this. Inequality, probability defined by inequality, is safer mathematically to reasonably define the probability, because one point may not have any meaningful probability. Also, I mentioned it 320, so if you don't understand what I'm saying, maybe let me know, then I can direct you. I can give you the link to the lecture. Anyhow, so the point here is, if you observe the population, then you can calculate the distribution. That is easy, but the problem is you don't observe the population. So even if there must be some true distribution, population distribution, but you don't know, you don't have that information. Then from there, how can we handle? Then also from the population distribution, we can calculate these measures: mean, variance, standard deviation, covariance, correlation. They are expected value of something. All of them are like, so expected value of something, expected value of some kind of transformation of the random variable is the common factor of these measures. And statistically, we call them moments. But so the term moments is not important, but it's another name for expectation, different kinds of expectations. And you know what they are. Mean is the expected value of the variable itself. So usually we write it as expected value of y, or Greek letter mu stands for the true mean. So remember, this is calculated from the population distribution, or you calculate this mean if you were able to observe the full population. Then you are going to get mu of y. So we use subscript y because if there are other variables, then you'd like to distinguish which mean this mean is for this variable. Okay, so and the textbook says it as a long run average. So as you repeat the calculation forever, infinitely many times, then you are going to get this. And variance is defined in this way. Y, the random variable, is subtracted by its mean. So inside the square is inside the parentheses is the distance from the center. How much of value or random variable may deviate from the center, the mean, and take square because the deviation could be negative. So we would like to make everything positive by taking the square. So then you may interpret this square as the distance from the mean because everything is positive, and the further from the mean, the larger this value would be. And this transformation is taken by expectation is taken on this transformed value, and we denote it as sigma squared. It's Greek letter sigma squared subscript y, and it is a measure of the spread, how spread out the observations are, how the spread out the school districts are on the population distribution. And as you know, standard deviation is just the square root of the variance. So because we have taken square, we'd like to recover it back to the original scale using square root. And you don't need to know this, but let me just explain briefly. I mentioned briefly in 320 about skewness. So skewness itself is not important. It's useful because it captures asymmetry of the distribution. So if skewness is 0, it means the distribution is symmetric. But if skewness is positive, that means there are some extremely large values in the distribution. If the skewness is negative, it means there are some extremely small outliers in the distribution, or so either tail is longer. But okay, that's okay, but what I want to show you here is you have fourth order, third order, second order, first order. So it's purely mathematical generalization. So so we call them moments. The moments are different forms of expectations, and you can just think them as first order is mean, first order moment is mean, and second order moment with a little bit of manipulation is variance, and third order is skewness, fourth order is kurtosis. I don't think it's important. Kurtosis is about the thickness of the tail, but not so important, I guess. Anyhow, so when we see those measures, we will talk about that later. And these are examples. So these first three A, B, C are not skewed. This is slightly skewed to the left. So do you see? This left tail is a little bit longer. It does not drop rapidly as the right side. So it's skewed. It has a negative skewness, skewed to the left. And this is very severely skewed. The left tail drops quickly, but the right tail does not drop as quickly. So longer tail on the right, so the skewness is positive. And kurtosis. Kurtosis, if you compare these two, both are symmetric, but the second one has thicker tail. So the tail is very close to 0 here, but there is some kind of positive mass on the tail. So that's what the measures capture, and I don't think they are important. The skewness and kurtosis are not important, but it is nice to see them to understand how we define new measures and how to understand the expectations and moments. Okay, I'm going to call it a lecture. So I'm going to continue from here in like next week, right? And see you later. Bye. Have a nice weekend.